Binomial distribution. For binomial distribution, there are 4 conditions that we have to meet. The first being, we have to have 2 categories. Most often we think of these as success and failure. Keep in mind that in probability, success is sort of defined by the problem itself or the situation that you're looking at. If you're watching to see how many people run red lights at an intersection, then in that sort of situation, your success would actually be a legal failure, right? So it just kind of depends on what it is that you've got that you're looking at. A fixed number of observations. So it's not something you're going to observe endlessly. Has to be independent. Each observation has to be independent. The answer must be yes. And lastly, the probability has to be the same for each observation. I have this written off to the side. We'll see if that comes into play later. X is binomial, n number of observations with p probability. So this is your binomial. Number of observations and your probability. So what I want to do at this point in the notes is actually do a couple of problems. The first one being 8.1. Get to that one. 16. It's quality control. It says, an auto manufacturer chooses 1 car from each hour's production for a detailed quality inspection. One variable recorded is the count X of finished defects, dimples, ripples, etc. in the car's paint. So we have 1 car tested every hour. X is the number of paint defects. And what we want to decide is this binomial? let's see, two categories, success or failure. Fixed number of observations, independent, and the probability has to be the same for each observation. Is there a fixed number of observations in this? No, it's just every hour, right? Every hour that the cars come off the line, they pull a car. So in this case, it's not binomial because there's not a fixed number of observations. It's 1 per hour, but we have no end in sight to when they stop this process. So in this, we would say not binomial. And it's because there are no fixed number of observations. Let's look at 8.2. Polling a jury pool. So we're looking at a jury pool. The pool of potential jurors for a murder case contains 100 persons chosen at random from the adult residents of a large city. Each person in the pool is asked whether he or she opposes the death penalty. X is the number who say yes. Okay, let's see. We've got 100 persons. Do we have two categories? Yeah, whether they oppose or don't oppose the death penalty. So two categories. Yes, no, death penalty. Fixed number of observations. Yeah, there's 100 observations, 100 subjects. Is it independent? Yeah, presumably it would be independent. People tend to be independent. The probability, is the probability the same for each? Well, they're going to say yes or no. Well, I guess they could say, oh, no. You always have that wishy-washy guy or girl. But you would assume that there is a probability for the population at large, that this particular town has a relatively fixed probability at that moment. So oftentimes we have to assume things in statistics, and this is one of the ones where we would assume that the probability is a fixed amount from individual to individual. So in this case, we have to make an assumption, but it seems a reasonable one to make. Okay. Everybody okay with those 4 things? Yeah. Don't be afraid to make an assumption in this class. I know that really doesn't fly in most other math classes, but if you can back it up with some logic, and you want to try to back up something like that. I mean, if you're that close, don't try to argue the opposite so much as maybe try to see if you can find ways to argue why it would be binomial, if that makes sense. And if you can't find a good argument for it, then say no, it's not. But if you can think of something that's reasonable, like, well, it seems reasonable that the city would have some fixed probability of that. All right. Okay. Now, moving on to the next bit of notes. The binomial coefficient. What's a coefficient? Anybody? Coefficient is a multiplier. It's just it's some number that you multiply to get somewhere else generally. A lead multiplying number. This is the number of ways arranging k successes among n observations so k being the number of success events among n observations. It's written like this: n over k, that is the binomial coefficient. It's calculated like this: n factorial over k factorial times n minus k factorial. Do you guys know factorial? I don't believe we've talked about it in this class. But factorial works like this. This would equal 3 factorial would be 3 times 2 times 1 times, oops, not 0. That's a problem. 3 times 2 times 1. So when we were dealing with the card problems, we can use this in card problems as well that we were doing in Chapter 7. I didn't introduce it then, but there's a way to make this work for the card problems. Where how many ways can you pick a card, or a certain number of cards? That'd be like 52 factorial, which is huge. So factorials grow pretty quickly. You need to know this: 0 factorial is 1. Not entirely sure I know why that's true, but we need to know it. So let's look at an example. Let's say I had 5 observations and 2 successes. I'm looking for the probability of 2 successes. So this would simplify to this: 5 factorial, that's your n, over 2 factorial times 5 minus 2 factorial. Which would simplify slightly to 5 factorial over 2 factorial times 3 factorial. And this would then become 5 times 4 times 3 times 2 times 1, where the 1 is really not necessary, because 1 times anything is that thing. 2 times 1 times 3 times 2 times 1. And then we can do some simplifying here. You can cancel the 1s, but they don't really cancel. The 2's cancel, the 3's cancel, and this 2 cancels with this 4, and it becomes 2 there. So what we get for an answer is 10. There are 10 ways that I can, what this is saying is there are 10 ways that I can take 5 somethings and arrange them 2 at a time. Okay? So now let's go to the fun stuff. That's just the coefficient. Now let's look at binomial probability. Probability that x equals k. This doesn't always have to be an equal. It can be an inequality. We'll see examples of that. It's written by the formula n over k, which is the binomial coefficient that we just looked at, times the probability of the kth term, times 1 minus probability to the n minus k. Alright, so I'm going to do an example, but it's one of the problems from the assignment today. 8.6. Let's see, that is on same page. Oh, I take it back. It's not one of your problems today. It is on page 519, and it's defective switches. So the problem says the number x of switches that fail inspection in example 8.3 has approximately the binomial distribution with n equals 10 and p equals 0.1. The probability that no more than one switch fails is, okay, so n equals 10. We're taking 10 switches at a time. The probability is 0.1 to fail, and the question is, what's the probability that not more than one switch fails? More than being an important idea in this. So what we're really asking here is not the probability that one switch fails, but what's the probability that one or zero switch fails, because it's not more than one. So we have to look at this from an inequality point of view. What's the probability that x is less than or equal to 1? Which is going to ask us to figure the probability that x equals 0 plus the probability that x equals 1. So here's where we go from there. The probability that x equals 0 is going to be this guy. 10 switches, 0 failures, this is our coefficient, times the probability to the k power. 0.1 is the probability. What's the k power? That's the 0, how many fail, times 1 minus the probability that we have a failure, times n minus k. that's written out in this form. We'll modify it in the next step. But before I do that, I'm going to do the same thing like this, because that's going to be plus this other probability. 10 switches, 1 fails. The probability of a failure is 0.1. I'm going to raise that to the k power, which is 1 in this case, times 1 minus the probability that 1 fails, 1 minus 0.1 to the 10 minus 1 power. So this thing right here becomes 10 factorial over 0 factorial times 10 minus 0 factorial times 0.1 to the 0 power. What's any number to the 0 power? 1, right. So this is 1 times 1 minus 0.1, which would be 0.9. How about I put some x's in here? Sometimes stats makes more sense with x's than dots. And 10 minus 0 would be to the 10th power. Plus, this is 10 factorial, 1 factorial times 10 minus 1 factorial. Thank you. Hang on a sec. Tomorrow, perhaps. Yeah. 0.1 to the first power. And this is going to be 0.9 to the 9th power. Well, 0 factorial is 1. Good. So 10 minus 0 is 10. So this is 10 factorial divided by 10 factorial. This whole thing here is just 1 times 1 times 0.9 to the 10th power. Plus 1 factorial is 1. 10 factorial is 10, 9, 8, 7, 6, and all those numbers. 10 minus 1 would be 9 factorial. So 10 factorial over 9 factorial, it's going to cancel out everything past the 10. So the 9, the 8, the 7, the 6, and so forth are all going to get canceled out by this. So this just becomes 10 times 0.1 times 0.9 to the 9th power. And then we go to the calculator. 0.9. So I get that this piece right here is 0.3487-ish. And this is about 0.3874. When this boils down, this just becomes 1 again, pretty much. Add those guys together. So the probability You guys got all that? I know that's a little tricky. You'll have to play with that a couple of times. I do have another example in here. It's, I think, just kind of going through the same steps. Would you rather I not and let you go through it yourself, or do you want to go through another one together? I'll let you guys pick. Just for fun? Just for fun. All right, Michael. For you. All right. Okay. All right, let's go through. This is one of your problems. This is 8.8. You know, I thought it was, and it's not. It's actually an example from the book that uses one of the numbers that we have for today. So my apologies. But this is from the assignment. This is on page 519, and it's broccoli plants. And I can think of no plant I would less like to study. But here it is. So it says, suppose you purchase a bundle of 10 bare root broccoli plants. That would never happen in my house. The sales clerk tells you that on average you can expect 5% of the plants to die before producing any broccoli. Assume that the bundle is a random sample of plants. Use the binomial formula to find the probability you will lose at most one of the broccoli plants. So we buy 10 plants. We expect 5% to die. And the probability is, what's the probability that x is less than 2? Let's see. So that's how I chose to write this. You could also write this probability as the probability that x is less than or equal to 1. These would be equivalent statements. Okay? So n is 10. Probability is 0.05. And k in this case is how many die. And this would be either 0 or 1. So it's going to have a similar setup to the last problem, the example that we did, where n is 10. The first coefficient is going to be that 0 of the plants die, times the probability that a plant dies, to the k power, which in this case is 0. This is n over k. Okay. Times 1 minus the probability that 1 fails, times n minus k. And I have to add that to the probability that 1 fails. So that's going to be 10 purchased, 1 fails. 0.05 is the probability that 1 fails to the first power, the k power, times 1 minus the probability of a failure. Oops. That's not going to work well. To the 10 minus 1 power. So this is going to be 10 factorial over 0 factorial times 10 minus 0 factorial. Any times, not equals. Any number to the 0 power is 1. And this is going to be 0.95 to the 10th power. Anybody remember what that's going to be? That's 1, right. Yeah, this is 1. So what we end up with here is just 0.95 to the 10th power. And this is going to be 10 factorial over 1 factorial times 10 minus 1 factorial, which is going to be 10 because 9, 8, 7, 6 and all that are going to get canceled out here. If you're unsure about that, call me over and I can show you that. Times 0.05 to the first power times 0.95 to the 9th power. So this is 0.95 to the 10th power plus, oops, no, I don't want the plus up there, plus, this is going to simplify to 10 times 0.05 times 0.95 to the 9th power. So what that tells us is that there is about a 91% chance that no more than one plant will die.